Hi, my name is Ineta, and today I'm excited to present my computer vision project titled Generated Content Detector. In this project, I created a system that accurately tells the difference between real human faces and AI generated or altered images. This tool aims to protect people and society from the dangers of manipulated images like stolen identity, deepfake media, and the spread of the false information. As technology improves, it gets harder to tell real content from fake, so it's important to develop systems that can detect and reduce these risks. So let's begin with a brief overview of my GitHub. This README file contains a more detailed description and explanation of my project. And I would like to emphasize that I dedicated a considerable amount of time to creating this data set. Initially, there was one source and it contained photos that were similar and closely resembling each other. So, to enhance its diversity, I combined images from four different sources. Here is they listed, because I wanted to train a strong model that works well with new data. So as a result, I ended up with a balanced data set with 5,000 real and 5,000 AI generated images. And although this may not be enough for a complex project, I believe this number is reasonable compromise given the time and processing limits. So in this project, I use three different approaches, and codes for them you can actually find in the notebooks files. I think it will be easier that way. Here they are. And a model A, in this case, is a custom CNN. All layers are initialized there from scratch, but I will provide more details when I run this code later on. For now, I just want to briefly explain the other models. So model B, actually three of them, it focused on transfer learning and features similar to Model A CNN architecture, but takes a different approach. It uses weights from the pre-trained models to enhance learning, and some layers are actually frozen to help the model adapt better to my specific task. So I won't run each of the code individually since they're quite similar. Instead, I've summarized all the key outcomes in a results section over here. And specifically, I used the EfficientNet, ResNet, and the Vision Transformer. And more details on each will also be on the README files. I just don't want to repeat myself, just will go briefly. And the last model, C, is a statistical model, and it's probably my favorite one because it employs many concepts that we discussed in class. In this approach, we define features directly instead of using CNN. And it means that images are converted into numerical data by extracting important statistics. But once again, I'll provide more details when I actually run the code. I just would like to point out that here is another file called readme reproducibility. Basically, this file states that if you run any of provided codes in Google Colab, I mean these five provided codes, so this file just goes in little details, but essentially it just says that if you run it in Google Colab using any of the available GPUs, there should be no additional setup steps required. I've tested this process on several computers to ensure it's reliable. The only exception will be Model A because it's a custom-made and requires like to indicate the input to save the model. Like over here, after you run the cell, it's important to set the local file name and path where you want to save this model being saved, likely within the Google Colab itself. So let's actually go to that Model A and start running cell by cell. So starting with importing libraries. That shouldn't take long. And then I'm gonna download the dataset. Yeah, just 10 seconds. So downloading the dataset and then unzipping it actually also doesn't take much time. Even though there are 10,000 photos, these two functions doing it really, really fast. So this is almost halfway through. Almost there. Now we unzip those photos. That's very fast as well. Okay, it's done. Here, I just want to make sure it's CUDA, so for faster processing times. And next step will be preparing, basically splitting dataset into three parts. So it actually will probably take 3-4 minutes. So I'm gonna pause for now and come back when this cell is done so we can continue. So it actually only took 2 minutes. So let's run the next cell. And here I am displaying the training and validation images with their labels, which is important for confirming the dataset is loaded correctly and checking for errors like corrupted images. And it also helps illustrate the diversity of the data. Uh, this is an important section where I actually define my simple CNN model, and it consists of the two convolutional layers, two max pooling layers, and three fully connected layers. It is initialized to extract features from images and then reduce the spatial dimensions. And the fully connected layers take the flatten data from the convolutional layers and generate the scores for my two classes. And here I'm just making sure that the model is moved to the GPU to accelerate the training. Now, let's just define the loss function in optimizer and do the actual training. Okay, it's gonna take a little while. So the process is now complete. It took nearly 9 minutes, and the model stopped at the 18 epochs to prevent the overfitting as the validation loss began to increase. And this is to avoid the excessive fitting to the training data. Learning curve helps to visualize training results, and the training loss decreases steadily. You can see it here in blue, indicating the model is learning well, and the validation loss in orange also decreases, but kind of starts a little bit to plateau after about 8 epochs. But still, this suggests that the model is generalizing well without overfitting, as the gap between the two losses remain pretty small. So overall, this indicates effective training. It probably could have been a little bit less epochs, but my code is set for the automatic early stopping, so I do not control the amount of the epochs, but that's just my personal opinion looking at the graph. And the validation accuracy right here supports this point. It's showing that the model applies well without overfitting. Here is a little bit of the tricky part because we need to enter the local path. Let me just run. Yeah, it's here. I'm just gonna copy my local path because we need to enter it here to run the model. To save it, I'm sorry, to save the model on a local computer, which is Google Colab in my case. So it's a model saved successfully, and now we can load the model. Yeah, it shows its architecture. And the last part is just basically several tests to check how well the model works. And here will be, yeah, here they are. Just some random photos with predicted and actual labels. And looks like the model is doing a pretty great job. True and predicted are all aligned. The overall accuracy. It shouldn't take long. Okay, it's 96.55, which is impressive. Classification report also should show great results. Yeah, precision and recall on both AI and real. Um, just to clarify, I have real color in here because originally I had the real in black and white and the real photos in color. So I used only the color ones. That's why it keeps showing up as a real color, which means real photos colored. It was just too much work to change. I have a lot use this terminology in a lot of places, and just was not enough time. If I had a little bit more time, I would have removed the word color everywhere. And confusion matrix, which is the last part, should be also very good. Yes, it's misclassified just 20 and 49, so indicates few mistakes. So overall, the model is very accurate and reliable in telling the classes apart. And I just would like to show the other model, the statistical model. Um, while it performs slightly less impressively than my Model A, it is much more relevant to the content of our class. That's why I want to show it. And it shows a lot of what we've covered through the semester. And this model uses traditional machine learning techniques to analyze statistical features extracted from the images. Let's quickly run this model. And here in this section, I'll be defining 9 different helper functions, which extract important features and statistics from images. They provide insights into frequency distribution, check edges content, evaluate texture, measure noise levels, and also give like overall intensity data and put together a complete feature vector, helping with the image classification analysis. Each of them has a short description of why exactly I chose them specifically. And now I'm gonna download the same exactly dataset that I used previously, consisting of 10,000 photos. And I'm gonna unzip them and split this data into the train validation and train sets, just like previously. So I'll pause for now because it's gonna take a little while. Well, it actually only took 1 minute. So now we can build the feature matrix. And here I will be defining classifiers. Basically, this code defines various machine learning classifiers for the classification tasks, each with specific configuration to optimize the performance. And these classifiers will be used for training on the extracted features from the images. And here are the 7 different models that I chose to use. So once this is done, I'll run this cell. So building feature matrix took 6 minutes, and now we can move on to training. The training actually took less than a minute, and you can see here below that gradient booster is the best model. It is such learning method that builds decision trees one after another, and each tree tries to fix the errors of the previous one, improving the accuracy. So it's a good for classification tasks. It captures complex patterns and is flexible for various data types. So I'll use this model, the gradient booster, to evaluate performance of the test set. I'm going to run this code now, but I will actually show the comparison data in the results section where I compare all 5 of my models. So for now, I just will quickly finish running this. Here is the classification report. Checking for overfitting and testing on a full data set now. Simply here at the end will be beautiful, like a visual representation of the results on this model. So hopefully it will run quick. It's supposed to be pretty quick. Yes. Once again, I'll compare this in a one table with all 5 models. I use the same numbers. And visual part. Okay, you can actually see that the predicted and true are extremely accurate. Oh, here, this photo was wrong, for example. It was predicted as AI, but it's actually a real photo, and the rest seem to be... Oh, here is another example of misclassification. But if you look at the AI, they're actually all absolutely accurate in here. So now, the last step. Let's compare all 5 of my models in the results section. The statistical model showed strong performance with a high accuracy in both validation and testing and F1 scores. It overall has a very good fit to the dataset and effectively captures all the underlying trends. Overall, you can see that all of the models nearly achieved the perfect performance in my dataset. And while these initial results appear promising, I do have recognized that the performance reported by the models may not reflect the realistic capabilities due to the limited diversity. It was sourced from the 4 channels, yeah, and they may not capture all the real world scenarios. Additionally, there is a risk of overfitting due to the small data set size. While 10,000 photos may sound quite a lot, but I think for a project like that, it should be hundreds of thousands, if not million photos. So because the model may memorize the training data rather than identifying the underlying patterns, and that would result in excellent performance in training and validation sets, but would struggle with the new data. And I actually tested manually about 100 random photos from the internet just for myself, and found that my model A, which was built from scratch, performed really well even on those. In contrast, the other models didn't do quite as well. So, to improve the performance in the future, I would plan to implement more different strategies like cross validation, data augmentation, and use an external, more different external data sets to develop models that would work well in real world situations. But to be honest, I just struggled to find so many different data sets on specifically just photos of the faces and portraits. So there were really more just like 4 sources. So it's really challenging and limited as of now. But overall, I'm very happy to have achieved such great results with my current models in such a short period of time. So I guess that's it for today, and thank you for your attention.